Hello and welcome. My name is Dibayan Bhattacharya. In this presentation, I am presenting our work, Supervised Contrastive Learning to classify paranasal anomalies in the maxillary sinus. Now coming to our clinical use case. In our study termed the Hamburg City Health Study, elderly people in the age group of 45 to 74 years received MRI for neuroradiological assessment. As a first step towards automating the study, we detect anomalies in the maxillary sinus. As can be seen in a diagram on the right, maxillary sinus is a type of paranasal sinus characterized as hollow spaces in the bones around the nose. One of the main functions of the maxillary sinus is to make mucus to keep the nose from drying out. However, incidental findings are commonly observed in this hollow space. As such, we wish to segregate patients into healthy and anomaly category by looking at the maxillary sinus using deep learning techniques. Here, we can see a zoomed in coronal plane images of healthy maxillary sinuses of 3 different patients. Mucosal thickening, polyps and cysts are the considered anomalies in our work. Now coming to the main challenges in this work. Here we can see 2 patients with 2 healthy maxillary sinuses, and we can observe that the right patient has a slightly larger maxillary sinus, as well as the shape of the maxillary sinuses are also different compared to the patient on the left. Second, since our dataset contains anomalies, it is also important that the classifier does not overfit to a particular anomaly. Specifically, we have an uneven distribution of the 3 anomalies in our dataset. Further, these anomalies have huge variations with respect to their appearance. This can be particularly seen with the polyp and cyst anomalies, where the polyps and cysts are differently located and have different sizes. Therefore, it is incumbent that we learn anomaly invariant representation of the maxillary sinus for volumes exhibiting anomalies. Now coming to our dataset, we have flare MRIs. The label dataset consists of 119 flare MRIs, of which 106 patients have normal maxillary sinuses and 93 patients have abnormal or anomalous maxillary sinuses. All the anomalies are grouped into a single class called anomaly, and all the normal maxillary sinuses are grouped into a single class called normal. Now coming to our pre-processing steps, there are 2 stages in it. First, we extract the maxillary sinus volumes from the larger head MRI of each patient. Secondly, due to the symmetry of the maxillary sinuses, we flip the coronal plane of the right maxillary sinus to give it the appearance of the left maxillary sinus. Here is an illustration of our approach. With the aforementioned challenges of learning anatomy and anomaly invariant representations, we employ supervised contrastive loss with cross entropy loss as an auxiliary loss function. We do so by having contrastive heads and classification heads, respectively. The red dashed lines here represent features being pushed apart from one another, and the green dashed lines here represent features that are pulled towards one another. The supervised contrastive loss forces the neural network to learn a single representation for the anomaly and normal maxillary sinus volumes, respectively. We use cross entropy loss here to preserve the discriminative ability of our neural network. Here are the most important highlights of our experimental and implementation details. Here the scratch method denotes 3D ResNet 18 with randomly initialized weights. We observe that supervised contrastive loss leads to an increase in classification metrics. Additionally, our loss, which combines supervised contrastive loss and cross entropy loss, leads to a further improvement in classification metrics. In this slide, we show the AUPRC plot as well as the experiments with our held out training sets. Below, we see the TSNE plots of the contrastive learning methods. We see that the supervised contrastive loss has clusters which are more spread out, whereas our loss has clusters which are much more compact. Now coming to the discussion and conclusion. Number 1, we propose an end-to-end algorithm for anomaly detection in the maxillary sinus. Number 2, clustering based on class priors is helpful to learn representations that overfit less on the training set. Number 3, we also show that the combination of cross entropy loss and supervised contrastive loss improves the performance of the model as it learns anomaly and anatomy invariant representations. Number 4, compared to the other works that use deep learning for paranasal inflammation study, ours is the first work that tries to achieve label efficiency and thus attempts to reduce the workload of physicians. With this, we come to the end of our presentation. Thank you so much.